See here, you guys. Waiting for the chime. Okay, there's the chime. It looks like I'm recording. Let's check to make sure I'm real time. Okay, that looks pretty good. Okay, I think we'll have decent sound quality this lesson. All right, you guys. So today's lesson is a review of limits. You did limits last year, and I know that was 5 months ago, so let's refresh. There are 8 powerful methods for evaluating limits. This is not an exhaustive list of every possible thing you can be expected to know. But these are the best techniques that you should use. First of all is simple substitution, you guys. Just try to evaluate this directly. I wouldn't do it right here because you can often run into problems where you're dividing by 0, and you really shouldn't be using the equal sign in combination with the division by 0. So I would do the evaluation offline. I would do the algebra offline. So simply try substituting in a 5. And the danger is you get a 0 in the denominator. That's really when you run into problems. So 2 times 5 plus 1. What is that? 35 minus 3 over 10 plus 1, or 32/11. So since it works perfectly with no issues at all, you can simply use evaluation. The function is defined at 5, and so you simply plug in a 5, and there you go. And there's your answer, and that's all the work you need to show. You've justified your answer here. Okay, second one, algebraic manipulation. This one's a little different. If you directly plug in a 4, radical 4 over 2, and then 4 minus 4, you end up with some issues here. You'll notice that this is a 0, and you notice that that is 2 minus 2, which is also 0. I'm hesitant to write equals 0 over 0. I hate to use equals 0 over 0. As long as you say it's in indeterminate form on your paper, hopefully that'll give you an allowance. You're never supposed to use the equal sign with something that's undefined. You just describe what's going on. So here we have a 0 in the numerator and a 0 in the denominator. So one way of handling this issue is actually L'Hopital's rule, which I'll talk about later. But you should be familiar with this idea of manipulating this expression algebraically. And unlike how you usually do things where you rationalize the denominator, in this case, we're going to rationalize the numerator. And so this expression, radical x minus 2 over x minus 4, usually the way to clean these things up is to look at the denominator. In this case, I'm going to multiply the top and bottom by the conjugate of the numerator, radical x plus 2 over radical x plus 2. This is basically just 1. And so I'm going to try this out here. And if I FOIL what's in the numerator, I have radical x times radical x, which is just x. And then I have radical x times positive 2, 2 radical x, negative 2 radical x, and finally, negative 2 times positive 2, which is negative 4. And that is over this, which I'm not going to FOIL out. And you'd think, well, why are you doing, how do you know, or why don't you do that one? And the reason is just from experience, from doing so many of these, you get to the point where you recognize we will worry about the numerator, not the denominator. So if you simplify this, notice I'm not using limit notation down here because I'm just doing some algebra work and I don't need to worry about copying limit, limit, limit on each step. These go out right here. And I end up with x minus 4 over x minus 4 times radical x plus 2. And if that's the case, you can think of this as being multiplied by 1. If that's the case, you can cancel these as long as x minus 4 does not equal 0. In other words, as long as x does not equal 4, I can say that this is the same thing as this. Okay? And you might say, well, wait a minute. If x equal to 4, you'd be divided by 0. That's why I have this restriction here. And you might say, but wait a minute, that's the exact value of x that they want me to use in the limit. So does that get me in trouble? Well, yes, if you use direct substitution on this expression. But remember, this is the limit as x approaches 4. When you approach 4, you're never going to get exactly to 4. You can be really, really close to 4. As a matter of fact, you're infinitesimally close to 4, but you're not at 4. And so where x doesn't equal 4, it doesn't exactly equal 4. It's something extremely close to 4. So we're actually allowed to rewrite this limit. And so be careful how you express this. Because of this algebra work I've shown here, this is identical to the limit as x approaches 4 of this expression, radical x plus 2, like so. Okay, and so now this is kind of sneaky, and this is why it took hundreds of years to develop the concept of limits. I just said x wasn't going to be equal to 4, and now I'm kind of going back on my word. Well, in this case, I can use direct substitution and simply plug that in there, and so I'm allowed to just substitute and say 1 over radical 4 plus 2, or 1 over 2 plus 2, or 1/4. Okay, and so there's my limit. I've justified my work. Okay, and it's really kind of sneaky because here we said, okay, this will be this equal to that as long as x doesn't equal to 4. And then we said, okay, well, x isn't equal to 4. It's really close to 4. And so then we used this idea, substitution, to evaluate this limit, and we got away with it. Okay, and so limits are sneaky, but that's what they were designed to do, is to get you out of these jams of dividing by 0. And sure enough, if you type this into your calculator, you'll find indeed that you do in fact get 1/4 as you put numbers in closer and closer to 4. Okay, excuse me, sign diagram. All right, in this case, if you look at what happens here, if you put in a 3 in here, if you try to substitute in a 3, you end up with basically a 3 over a 3 minus 3. And this is finite, not 0. Finite, but it's not equal to 0. And this is basically going to approach 0. Okay, and so you have a real problem here. You're dividing a finite number by 0, which is undefined. 0, depending on whether it's closer to positive or negative, is going to either make a quotient that goes up to positive infinity or negative infinity. And so we want to establish what's going on here. The shortcut answer of this is you can simply declare that it does not exist and move on, because you're dividing a finite number by 0. It's undefined. I do think a sign diagram is helpful to get a little more insight into what is going on here. So if we make a sign diagram for this, you'll notice that the numerator is 0 at x equals 0, and the denominator is 0 at x equals 3. If I put a number bigger than 3 into this, I have a positive over a positive, which is positive. If I put a number between 0 and 3, like a 2 in there, I'd have a positive over a negative, which is negative. And then to the left of 0, we really don't care so much because we're only interested in approaching 3 from the right, right? This is 3 from the right, so we go in really close here. So in this case, what we have happening is we're dividing a positive 3 by a positive number very close to 3. And so that's going to go up to positive infinity. And so you can simply just say the limit does not exist because it approaches positive infinity. Okay, and I always think it's just good practice to justify your answer, give some explanation, and so on. If you simply write this, that may or may not, I mean, that is the correct answer, that limit does not exist. But you're not really justifying it in any way. And the sign diagram helps to make that justification. Okay, one thing I will caution you about that your book does, and I do believe this is sloppy and would cause problems later on, is they do use the equal sign for this. They will say in your book, the limit as x approaches 3 from the right, x over x minus 3 equals positive infinity. And I really caution you, please don't do that. That's going to hamper your future career in math. If you think of infinity as a finite number like any other, treat it as a finite number like any other, you really run into problems when you use equal sign in combination with infinity. I would beg you, please don't do this. It just causes problems in the future. Just never use the equal sign with infinity, and you run and then you don't run into as many problems. Okay. All right. Last one I'll do now before we get to the next video is dominant term analysis. The idea is here, as x goes to infinity, as x gets larger without bound, if you compare the relative sizes of those two things, you have a dominant term in the numerator. The dominant term of 3x plus 1 as x goes to infinity is 3x. Okay. Think about that. If x is 10, you have 31. I like to think in terms of dollars, right? If you multiply x by 10, you have $31. If you make x 1,000, you have $3,001. If you make x a billion, you have $3 billion, and then someone gives you one more dollar. You basically have $3 billion, okay? So this is driving the numerator of this. That 1 is really not going to matter as we make x increase without bound. And then same thing in the denominator. The dominant term of x plus the sine of x, well, x is going off to infinity, and we can never pin down the exact value of this. It's going to alternate between positive 1, and it's going to oscillate between positive 1 and negative 1 and every value in between. But this is much, much larger. 1 billion plus 1 or minus 1 is still basically a billion. So the dominant term of the numerator is just x. And so this limit is equal to the same limit, the limit as x approaches infinity of the dominant term of the numerator, 3x, over the dominant term of the denominator, x. And since x is not equal to 0, we can simply simplify this as the limit as x approaches infinity of just 3. And that is simply 3. If there's no x in this expression, it doesn't matter what value of x is, that fraction is always going to equal 3. And so that's your limit from a dominant term analysis point of view. Okay. All righty, guys, I'll catch you at the next video. Okay, folks, let me stop this here. Okay, see you later. Bye-bye.